The last thing we're going to look at with systems of equations this week is nonlinear systems in two variables. And again, we can do all of these same processes with 3 variables or 4 variables. That's just not something we're going to focus on in this course. And once you get into some higher level math classes, you'll learn some ways that make that process quite a bit simpler. So it's really not worth us spending the time to do that algebraically. So a nonlinear system is going to contain at least one equation that is not of the form ax plus by equals c. So it's not a line. Okay, that's what nonlinear means, is not a line. So here's a couple of examples. You can see this first one here, x squared plus or equals 2y plus 10. That's going to be a quadratic. So that's going to give us the graph of a parabola. In the second one, we have y equals x squared plus 3. That's a parabola. X squared plus y squared equals 9. You should recognize that as a circle. When you have, remember that in the beginning of the year, this was back in section either 1.9 or 1.10. I don't remember which one. The general form equation for a circle is x minus h squared plus y minus k squared equals r squared. So in this case, this would be a circle with a center at 0, 0 and a radius of 3 because that's r squared. So it's good to recognize that. It kind of helps you anticipate how many solutions you should have, but it's not a big deal if you don't recognize what the graph is going to be. So a solution of a nonlinear system in 2 variables is going to be an ordered pair, just like it was with the other. It has to be an ordered pair x and y that satisfies, again, both equations. If it works in one of them but not the other, then we cannot use that, okay? So the solution set of the system is going to be the set of all such ordered pairs. So what's different about these is there might be more than one ordered pair. With linear systems, 2 lines can either not intersect, they can perfectly overlap, or they're going to cross. So you're only ever going to have one solution. However, with these non-linear systems, I could have something like a circle that then I intersect with a parabola, and you can see that these 2 graphs would cross in 1, 2, 3, 4 places. So you would have 4 different ordered pairs that all would make that system of equations true. So that's what makes these just a little bit trickier. The same 2 methods are going to apply. We're going to use the substitution method and we're going to use the elimination method to solve these. So let's look at a couple of examples of each of these methods. So using the substitution method, we want to solve this system. So the easiest variable it looks like it's going to be to get by itself is going to be y in the second equation. So if I take this one, if I add y to both sides and then subtract 9, I'm going to get 3x minus 9 equals y. And so that's what I'm going to use to make my substitution. So again, up here, now I'm going to take out the y, and that's where I'm going to plug in 3x minus 9. So let's do that. I have x squared equals 2 times 3x minus 9. That's where we're making our substitution. And then plus 10. Now I only have x's, but you'll notice we have a quadratic equation here. So we're going to have to use some of our polynomial strategies for solving this equation. So we're going to work first on just getting it all cleaned up. So I have x squared equals 6x minus 8. Now with quadratics, we want to usually get it equal to 0. So I'm going to move everything over here to the left. So it's equal to 0 because I want to try factoring first. That's always going to be our quickest method. So we say what multiplies to 8 and adds to negative 6. This is going to give us x minus 2 times x minus 4 equals 0. So we get 2 possible solutions for x. Either x equals 2 or x equals 4. And so remember what we just found here then is half of our ordered pairs. We have the x coordinates. Now we need to figure out the y coordinates. And since there are 2 different x coordinates, then we have to substitute in 2 different times. So we're going to take each of these and substitute back in. And I'm gonna substitute into this one because it's already solved for y. So y equals 3 times, let's do 2 first, minus 9. So that's 6 minus 9, that gives me -3. So our ordered pair would be 2, -3. And then the second time, I'm going to say y is equal to 3 times 4, which was our other option for x, minus 9. So that's going to be 12 minus 9, which is +3. So 4, +3 is our second option. So our solution set is the 2 ordered pairs, 2, -3, and 4, 3. We have 2 ordered pairs. Now, if you were to look at the graph of this, you can see exactly where these are coming from. So the top one gives you a graph of a parabola that looks something kind of like this. And then the bottom equation is a line, and it crosses through kind of like this. So we get 1, 2 places where it intersects. So 2 ordered pairs does seem to make sense. Now, the last thing on these types of problems that we always want to double check is, do both of the solutions make both equations true? So with nonlinear systems, you do need to verify your solutions. You can do it in your head, you can do it with your calculator, but you do want to do that because it is possible that the algebra may have led you to more solutions than would be true. And I'll show you an example where this happens. But both of these do work. If we go back in and just kind of do a quick check and plug into both equations, let's do first the ordered pair 2, -3. So that would be 2 squared equals 2 times -3 plus 10. Does 4 equal -6 plus 10? Yes, it does. And then we check in the bottom equation. We already know it works in the bottom equation because that's the one that we used to get it. So we know that we're good there. And then we also want to check the same thing with 4, 3, plug it into the other equation to make sure that it also is true. So we want 4 squared equals 2 times 3 plus 10. So does 16 equal 6 plus 10? Yes, it does. So both of those solutions are good. Again, we didn't really need to test it in the second equation because we really had already done that here. That's where the y value came from, was the second equation. So, but that is an extra step that you do have to do on these because it is possible that one of them might be extraneous. Okay, let's look at another one using the substitution method that is a little bit more involved with your algebra. Okay, so using the substitution method, I want to use the top equation to solve. If I don't have to do any square roots or anything like that, that's definitely what I want to try to do. So for this one, I just added y to both sides. That seemed like the easiest thing to me. So x is equal to y plus 3. So now we have to substitute that into the bottom equation for x. So I have, instead of x, I'm going to put in y plus 3. And then I have minus 2 squared plus y plus 3 squared equals 4. Now, hopefully you can recognize from looking at that, the top equation is a line, the bottom equation is a circle. So you can kind of start imagining the different ways that that could intersect. It could cross through the circle, that would give you 2. It could be tangent to the circle, that would only give you 1 solution. Or they may not intersect at all, which would mean that there's no solutions. So now we need to simplify this down. So I get y plus 1 squared plus y plus 3 squared equals 4. Now remember, when you square a binomial, you can't distribute an exponent. When we do this, remember we have to square the first, square the last, and then we multiply y times 1, so that's 1y, and double it, so that makes 2y for our middle term. And then you always keep the sign here the same. So similarly, square the first, y squared, square the last, positive 9. This has a plus, so we're going to keep the plus. 3 times y is 3y times 2 is 6y, and that's all equal to 4. So now we just need to combine like terms, get this all set equal to 0. So there we go. And then I noticed that I can divide all of these things by 2. So I'm going to divide both sides of my equation by 2. That doesn't really affect the right-hand side, but it gets this to something a little easier to factor by doing that. And this does factor to y plus 1 times y plus 3 equals 0. So our two solutions are y equals -1 or y equals -3. So once again, we want to go ahead now and back substitute with those two values. And I'm going to plug them in since I need to know the x values now. I'm going to plug them in here because that just seems like the easiest place to put them. So the two solutions that I end up with then are 2, -1 and -3, 0. Now do make sure you pay attention to the order that you put your numbers in. The first values that we found were y, and remember that y has to come second in your ordered pair. So just be careful. Sometimes it's just kind of our nature to put the first number we found first and the second number we found second, but we actually kind of found the ordered pair backwards in this case. So you need to be careful with that. And now we want to do a quick check. We know that those two ordered pairs work in the top equation because we just used it. But now we need to do a quick check and plug into the bottom equation to see if both of those ordered pairs work. So here's part of the reason why we check. Because when I plug in that ordered pair -3, 0, I see that I'm going to get a number that's way too big that's going to equal 4. I'm going to have -5 squared plus 3 squared. That's going to be 34. Not going to work. But then I noticed, this is exactly what I was just telling you a moment ago. Since that ordered pair didn't work, I went back and double checked my work and realized I wrote my ordered pair backwards here. The -3 is the y and the 0 is the x. Now, when we plug that in, we are going to have 0 minus 2 squared plus -3 plus 3 squared equals 4. And that does end up giving us 4. So it really serves two purposes. It helps you check your work and make sure you did it correctly, because here I made the exact mistake that I warned you against. And then it also makes sure that you don't have any extraneous solutions. So this is why it's important to check. And I am a perfect example of that right here. So that's using the substitution method. And next we will look at using the addition method. Oh, if you want to see what this graph looks like, this graph is a circle and a line, we said. It ends up looking like this. We have a line here like this, and then we have a circle that looks like this. So you have those two places right here and right here. Whoops. Where they intersect. So those are what our two solutions represent.